Alright, I did another video recently on my lengthy project to restore a Heathkit IP-27 low voltage power supply, and I mentioned in there that the reason I did that was because when I was a teenager in Germany and I was just starting in electronics, a few of us students who were going to be starting the electronics curriculum were invited to come in and spend a summer building a bunch of Heathkits to outfit the new electronics laboratory with test equipment. And some other students plus a couple friends of mine who all signed up did exactly that. And the first two things that I built was an IP-27 power supply and an IM-25 FET or solid state volt ohm meter. I actually have clearer memories of this than of the IP-27, but I know that I built one of those too. So once I was successful in restoring the IP-27, I decided that it would be appropriate to acquire an IM-25 and give it a similar restoration. And just today this one showed up. I think I paid about $45 for it. The previous owner, which was I think just a thrift store, said it powers up and nothing else was known about it, but it looked fairly clean from an intact standpoint. It didn't look like it was abused, although it is quite dirty. The paint is awful looking on here, even worse in some ways than the paint on my power supply. It has some ownership stickers on it. Barcode that's faded. It's not as bad off in that regard as the power supply was. There's a small crack on the lens of the power supply, but it's not significant. The knobs look okay, but there's a lot of dirt, almost like soot, on the case. These stickers might actually be there from the thrift store instead of from a previous owner. They might have just been identification. So this is a very similar design. It's the same case design, although the dimensions are different, and it's much less complex. It does have a power cord on it. Unlike the other one, the power cord on this one looks like it's in decent condition. So the first thing I want to do is crack this open and see what the inside looks like. If it doesn't look completely beat to hell, then I'll probably go through a similar restoration process on this to what I did on the power supply, although because it's a simpler circuit with fewer parts and it doesn't have, you know, pass transistors to blow out and so on, I anticipate that it'll take less circuit restoration to get it working, as long as things like switches are intact. So that'll be the next step. So there's the top of the case off. You can see the batteries. I even remembered this from being a teenager, that even though this was AC powered, it had a ludicrous number of batteries in it. 2 different packs, all C cells, took a lot of batteries. And those are in there, but something is loose back there. I'm not sure if it's the battery connector. The other thing is that unlike the power supply, even though they're the same vintage, this one uses a circuit board for most of the components, except those that have to be mounted on the selector switches. And the meter is, I think, probably from the same manufacturer as the meter on the power supply, except that it has a much larger face on it. One nice thing that Heathkit did on this one, as opposed to the power supply where they put the calibration pots on the back, was all you had to do here is lift the top cover off, and the calibration pots plus a couple of calibration capacitors are all right there where you can access them while working the controls and looking at the meter. I always thought that was a fairly nice touch. There's a great big wheel on the front hooked up to a potentiometer and it's a multi-turn pot. You can just keep turning it because it's got a ball-bearing movement in it, like a planetary. Many turns of this big wheel result in one turn of the pot. And this is for zeroing out the resistance in the ohms mode. And it's also one thing that this meter has is on the DC ranges, at least, there's a 0 in the middle of the scale, and that is allowing you to read positive and negative input voltage polarities without changing a switch selection or reversing the meters. But it's necessary to adjust the circuit a little bit with this in order to get the meter centered at 0 when there's 0 volts. There is a switch to adjust between AC and minus DC and positive DC volts. In spite of this feature here, there's a volts, ohms, amps switch, or milliamp switch. And once again, Heathkit didn't bother in those days, at least, with proper usages of capital and lowercase letters. That should have been a lowercase m for milliamps. Don't want to say mega amps. There is a switch for off, line powered, and battery powered. And then, of course, separate range switches for voltage, ohms, and milliamps, so you can have different ranges set up and then just change between them here. In spite of that, it all looks like a pretty good design. Looks like it ought to be a pretty nice meter. What I remembered about these, though, is they were a bear to set up and kind of unstable and kind of annoying. And I think Heath dumped these pretty quickly and replaced them with newer ones. You know, this is right around the time when it was becoming feasible and affordable to put digital displays on meters. So I don't think this model lasted all that long before Heathkit replaced it with a totally different design. Anyway, I'm going to continue dismantling this. So I figured out what was rattling around inside. It was this. It's another thing I remember about this meter is that for the ohms range, even though it can be powered off of line or battery for the overall meter circuit, the ohms range still needs an excitation voltage, and for that purposes it uses a battery, and it must be a battery. It can't use the line voltage or a line voltage derived power source for that, at least according to the original design. One could certainly be rigged up. Instead, it uses a mercury battery. I think this type was normally used more for cameras, but they used it here. It's a mercury cell, and I think it's 1.35 volts. And I already anticipated that if this was in here at all, it was going to be corroded and leaky like this. And it's probably got some mercury on there, so I'm going to have to wash my hands. These aren't made anymore, and although you can buy new old stock, they're not apparently allowed to be manufactured anymore due to the fact they end up in landfills with the mercury in them. And there's a couple of replacement models that are 1.5 volts using alkaline technology. Not as good as the mercury cells, probably don't last as long, probably not as stable, but probably satisfactory. So I've identified a few sellers that sell the alkaline ones that I can scarf up a couple of those if I need them for this. As with the power supply, the original 3M bump-on feet have come off, leaving only the adhesive pads. So I'm going to have to remove those, and at least I have some replacements available. Okay, there's with the bottom off. A lot of open space in this. That should be the power transformer down there, and this will be the main electrolytic capacitor for the power supply filter, I think. There's the socket for that battery, and as expected, it's a mess. But the switch contacts don't look bad. I don't see anything that looks burned up in there, and I don't smell anything bad either. And there is this capacitor here and a couple Did somebody do a jury rig down there? Yeah, that's probably original. There's a transistor with one lead cut off that's being used as a clamping diode. And it looks like another one up there. I think that's all part of the original circuit. And there are some small electrolytics in there which I'm also going to want to replace. Looks like 2 of them there. There's a couple of fuses. And not much else. And here's with the back off. And it looks like at least some of the original C cells are in here and probably corroded. So let's see. I don't remember exactly how these worked. Here's the smaller battery pack with its end cap. It doesn't seem to be too corroded, but there is some light corrosion on this. These batteries here will go in the trash. And I've not been able to get, well, that's interesting, the Heathkit labels on the inside. Usually they wanted you to put those on the outside. Anyway, this big tube here, which looks intact unless it has some corrosion on it, I've been unable to budge these screws here. They seem to be totally corroded into place, so I'm going to have to take some more heroic measures to get those off. Luckily they're the same design as on the power supply, and I've got this supply of identical stainless steel truss head machine screws from Bolt Depot, so if I don't have enough stock, at least I know I can order some more to replace these various damaged or ugly looking originals. Well, using the cutoff wheel on my Dremel tool, I slotted one of the stuck Phillips head screws, and now I can turn it out with a straight blade. And that is trash. I have to do likewise to the other one. Well, it looks like all the coil springs in the battery holder are slightly corroded, even though there's no evidence of the batteries leaking. You know, the batteries are always leaking a little bit, but usually it's not enough to cause corrosion. But this is, you know, a fairly old unit, decades old, been sitting in here with batteries in it probably for a long time. And I can probably clean these up just with vinegar, with white vinegar, and put them back on. There are some wires that look tacked on there, and there's a blown foil, blown right off the board, or maybe it was cut and peeled off, I'm not sure which. And those are going to a place where it doesn't look like any foils used to go. And then there's a fuse holder. They're supposed to be, I think, screw-in types, but somebody just stuck the wire through and soldered them onto the clips, kind of kludgily. Same thing happened here. This is not marked to have a fuse holder, and the wires from the line cord are supposed to go directly up here, but somebody's, or up to here, but somebody's interrupted it, gone through this fuse and gone to here, which isn't a bad idea, but I wonder where the original fuse holder is supposed to be, if at any. I've ordered a manual for this and haven't received it yet. Somebody may have added that on later, possibly because they blew a foil off the board. I have to wait till I get the schematic in. I want to restore this the way it was. If it didn't have fuses, then it's not going to have fuses now. These 2 fuses, curiously, now this one appears to be a slow blow. It's got the spring in there and a little, I don't know what that is, a resistor or whatever they put in these. And it reads about 100 ohms. I keep dropping these, and this one here, which is marked as a little fuse, and I'm not sure what type it is. The label obscures most of it. Doesn't say slow blow or otherwise, at least not that I can see, maybe with my jeweler's loop. This one reads about 50 ohms, so they're not without resistance, and maybe that's correct for the type they are. But if I'm going to do away with these fuses, then I don't have to worry about whether these are good or not. They're certainly not completely blown. And I found this little grommet stuck in there. I have no idea what that came off of. So I'm going to put that aside. But I'm not sure if it's got something corrosive on it or not, so I'm not going to just lay it on top of my table saw, which I'm using as a workbench. I've got a plastic bag here that I think I'll stick it into. And this battery clip, the contacts are just absolute toast on it. I don't think there's any way to restore those. So I may have to come up with something else for this. Okay, I've got the case top and bottom, the bezel, the handles, those major parts that were real dirty, soaking in pretty warm soapy water, and also the knobs and little metal brackets around the handles are also soaking in a separate container. And since I've pulled the bezel off by loosening the side frame screws, I can now attack the front panel, which really just has kind of a sootiness on it. It doesn't seem to be otherwise dirty or corroded or marred, so I don't need to completely dismantle it like I did on the power supply. Okay, I've gone over all of these with a toothbrush and rinsed them, and now they're just soaking in clear water. I'm going to rinse them again, make sure all the soap is off. And the wash tub, after about 2 hours of soaking, the water's still a bit warm, and I've gone over it with regular toothbrush, which seemed to do nothing. So I did what I did on the power supply with a brass bristle brush, not rubbing too hard, but going over it in a circular pattern, forward or clockwise, counterclockwise, you know, scrubbing in all directions, going over it 2 or 3 times, and definitely removed a lot of gunk, but they still don't look very good. You know, there's just a lot of discoloration and blotches that aren't going to come off simply with a dirt treatment. So it's time to drain this and go on to the next step, and probably repainting. Okay, the chassis top and bottom, or case top and bottom, and bezel are air drying down here. I have rinsed and wiped off the knobs and the handle corner brackets. And over here, I've gone over this with several, first water wipe, then alcohol wipe, then dissolvent citrus cleaner, and then another alcohol wipe. And there's a couple of places where I got a couple streaks there I have to rub out, but that's the back panel, the front panel, the meter face, and just sort of de-dusted the circuit board, and also cleaned these side rails of the chassis. I'm going to take an inventory of the screws I need. Some of them are really corroded, some of them are in pretty good shape. Probably going to order a whole new set of the ones that show, and any one that's just corroded I'm going to replace as well. Have to figure out what to do about this battery bracket. I may decide to do a battery eliminator for that. Put a little sub-circuit board in somewhere. Wouldn't have to be very big. It could even be like a modern wall wart power supply. The thing is, I've heard that this meter is extremely susceptible to RF radiation. It'll really screw it up. So I'm reluctant to put a switching power supply in here, especially a cheap one, because it might really mess up the meter. So it might be better to just try to resurrect the battery clip here in one way or another. We'll see. I think I figured out what this little rubbery piece with the metal core is. This battery holder has no metallic part to the base of it. Instead, there's a metal part that makes sort of an L-shaped metal part with one wire soldered to it. Kind of hard to see it there. There's two wires. And then this other metal part that makes a bigger L and has another wire soldered to it. So I think the lower one pushes against the side of the battery, and this one pushes against the end of the battery. And those are both highly corroded. The whole battery holder is held to the circuit board with 4 bolts, and there was a corroded off head of a bolt that was laying loose in the chassis. I wondered where that came from. And then there's that rubber grommet thing, and I suspect that that grommet was the insulator between these two metal contacts, and that bolt head is what went through the core of it to provide the insulation while still mounting it securely. So I think that's what that is. I'm going to have to go online and see if it's possible to find a new battery holder for these things. And if that isn't possible, then I'm going to consider just making new contacts. They may just be copper. I'll go to the hardware store. I have to buy new paint anyway, and if they have strips of copper, which I'm pretty sure they do, in the right thickness, then I might look into fabricating something of this sort myself. Alright, I have the two contacts off the mercury battery holder in a Pyrex cup, and I'm going to soak those in some acid to see if I can get some of the corrosion eaten off of those. And I have the pieces in some muriatic acid there. Okay, there's the bottom panel after washing and drying. And here's the top panel. Definitely much better, but still ugly looking, almost looks burnt. So those are going to get painted over. And I'm going to do some very light sanding in a couple of these areas where it's gouged. This almost looks like something hot was put there, like a soldering iron touched it or something. And of course I have to go at it with some adhesive remover on the leftover sticky parts where the feet used to go on. So I've gone over the corner angle brackets that I'm going to repaint or paint over, and I've cleaned up with alcohol and lint-free cloths the top and bottom. They're looking about as good as they're going to, but not as good as I want them to. I've got all the adhesive off the bottom where the feet used to go. So it's time to hit them with the same paint I used on the power supply, which is Rust-Oleum Camouflage Ultra Flat in the 1917 khaki, which I don't know if that's their model number or if they mean that's the color of khaki in World War I in 1917. I'm not sure which, but that's what I'm going to use. It'll certainly match the other power supply on display. Okay, I've got the 4 handle brackets painted. And there are the descaled or pickled copper contacts for the battery holder. And I had hurriedly measured that out as 0.032 inches thick, and I got that, but it looks a lot thicker, so my micrometer was probably picking up more scale than I anticipated. I may have to go back and get a thinner sheet. So the first coat of paint has been applied to the insides of the case top and bottom. I'm going to hit one more coat near the front and rear edges where it overhangs slightly, and then I'm going to flip them over and put 2 or 3 coats on the side that normally shows. Now this base of this battery holder looks awful, so that needs some treatment. Alright, and there's the first coat on the outer surfaces of the top and bottom panels. And meanwhile, I've given another coat to the angle brackets. And then there's the second and third coats applied. Well, I didn't like the way these corner brackets came out. They had caught some dust or something and had lumps in them, so using the first 2 coats, or the 2 coats of dried paint that I added to it, I gave them a light sanding with a sanding sponge, and I'm going to reshoot them now. And it turned out I wasn't even using the right paint. I should have been using this satin enamel. First I was using a one that was matte, and that was way too matte. And then I had a gloss one, which was stupid because it shouldn't have been gloss either. So now I found the satin enamel that I'd used on the power supply. That was a good match for the original factory paint. So I've got to wipe these off with isopropyl alcohol and reshoot them. Okay, I've bought another piece of brass, this time .016, which is really close to what these originals are. Checking them with micrometer. It's showing a little thicker on here, but in some places it's showing a bit thinner, like .017. Anyway, I think it'll be close enough. I've cleaned up the original battery so that I can size the new carrier clips. The original one had a more complex insulator than I'm likely to come up with here, although I could do it if I really had to. It would just take more screwing around. What I'm thinking of doing is this is offset, it's not centered, and what I'm thinking of is to make one clip that goes essentially right on the one corner and makes the side connection. It'll push sideways, but the recess in there will keep the battery from pushing over. And then on the side that has a bit more clearance, I'll make an equivalent to this, which just goes up and contacts the top tab of the battery, like that. And unlike the first arrangement, which had one screw going through both layers with insulators, which is the part that I'd have trouble doing, I think I'm just going to go with one clip on one side and one clip on the other side, and the base will be the only insulator I need. And then the screws will go through the phenolic circuit board, which is also an insulator, so there won't be any shorting from that. I think this will be a more feasible way of me making the restoration of this. Okay, I've made 3 brass pieces. This is the side contact with a mounting hole and a small hole for wiring, and a bit of an angle so it presses up against the side of the battery. And then this is the main contact for the plus side. It's similarly set up with a mounting hole and a wiring hole, and then it goes up more or less straight and then has a bit of a down angle to it and a rounded head. And since this metal is a little bit thinner than what was on there originally, and I worry mostly about this right angle here straightening or bending too much and thereby making the battery loose, I've got this backup piece that'll double the thickness around this corner, and it goes on with the same mounting hole, kind of like that. And there's the pieces of brass bolted up. Obviously it's not on the circuit board yet, but there's enough bolt length to go through the circuit board. This top piece is obviously bent down more than it will be for real. I need to straighten this piece up a little bit before the battery goes in there. Okay, there it is. I think that'll work. It seems to be making good pressure contact on the side and on the top of the battery, and there's plenty of clearance between the plus lead here on the left and the side of the battery. I don't think it'll tip over. It would take quite a bit of pushing to get it out of there, but I might actually glue on a little piece of Mylar or something just to prevent short circuits if it does somehow tip over. That's probably a good idea, right on this vertical piece facing the battery. Just a little super glue and some Mylar probably. Okay, this is all cleaned up. I had a heck of a time getting the old adhesive residue from these two battery stickers off of the metal. I ended up using a combination of normal label dissolver and the Dissolve It product, and finally went at it with a safety razor acting like a small planer with some WD-40 as a lubricant, and that actually worked best. The original labels were very yellowed and were also very brittle when I took them off. They were pretty much falling off anyway, but parts were still sticking. So I scanned them, so I reduced them to two colors, not even grayscale, just purely black and white, and changed the grading so it would minimize the yellowing and discoloration. And then I did a little cleanup in places where it didn't come out correct, and then reprinted them to scale and stuck them down with my favorite adhesive for this kind of thing, Scotch Permanent Extra Strength roll-on adhesive, and rebolted the battery packs. Now, one cap on the 18-volt battery pack is broken, and I don't think it'll hold batteries. I think it'll just fall off, but I'm not planning on using it anyway. It's just installed here for authenticity. And I found out that I do need to use this 3-volt battery pack along with the 1.35 volt mercury cell for the ohms range. So I'm going to have to put a couple of C cells in here. I'm going to go to the hardware store, and I don't know if they make lithium cells in C size or not. Certainly in AA. I want something that's not too likely to leak, and the lithiums seem to be a lot better about that than do the alkalines. But I also have to make sure the voltage is appropriate. I'm a little concerned about the 1.5 volt alkaline replacement I got for the 1.35 volt mercury battery. Because of the way it's used in the circuit, It's used to bias the constant current source for the ohms range, and it might push it outside of tolerance, being, you wouldn't think 1.5 is that much higher than 1.35, but I have to presume there's some adjustability in the circuit to dial in for lower voltage and maybe also for a bit higher. I'll find that out when I actually fire it up. If that doesn't work, then I'm probably going to have to look at a battery eliminator for that, and probably for this one as well. But for the meantime, I'm going to go with the presumption that these are in here for decoration and possibly for functionality as well. So I've gotten pretty much everything except the new stainless steel truss head bolts I've ordered. Everything else has been repainted and repaired and so on, except for maybe the circuitry. I did use some contact deox on the rotary switches, and didn't show that, but I did it. And so I need to probably remove these fuse holders. These were jury-rigged in here by a previous owner. I did get the manual in that I ordered, and it showed that there were no fuses originally in this, certainly not for the amps range or ohms range or wherever that other one was put in the circuit by the previous owner. And then this other one was jury-rigged in here as a line voltage fuse. And I may actually do something like that, but I'm not going to do it the kludgy way the previous owner did it. I might just drill an extra hole in the back and mount a chassis fuse holder, do it properly. Or I might do something else, haven't decided yet. I'd really like it to look authentic and not have extra holes in it. So I'm going to look at my options on that. Alright, my alkaline based replacements for the original mercury cell arrived. The alkaline one's on the right, the original mercury one's on the left. Very similar. The heights seem to be the same. And I'm going to do a test using my pulse load battery tester. Shows 80% full. I'll try that again. Whoa, that's not reading so good. It's all over the place. I suppose it's possible that these may be designed to operate a little differently. And even though they're alkaline based, I don't know if there's some way they could have gotten it to produce only 1.35 volts instead of 1.5 volts, which would be the normal. And that may be why the tester is reading it low. Firing up my old non-high impedance multimeter that I had as a teenager. I could go get one of my Simpson 260s, but this is more readily accessible at the moment. Okay, on the 5 volt scale, which is the lowest one, it's reading 1.5 volts. I had actually ordered 2 of these because they came in sets of 2 from the eBay seller. And the other one tested exactly the same as the first one on the pulse load tester. I'm going to presume that they're okay at this point, even though they do seem to be reading a little low. And I've got a little piece of mylar there being attached with rubber cement as an insulator to the vertical part of the top battery clip. Okay, there's my insulator. And I've decided to put this chassis mount fuse holder, which I had in my junk box, inside the back of the meter, close to where the power line comes in. So from the outside, the only blemish will be the small 440 screw I've got going through there. But it can rotate. There's no keying on this, so I'm going to put a dollop of epoxy on there as well, just to keep it from swiveling around. Okay, the fuse holder's in there, and for the moment I'm just going to snap the original power fuse that came with this meter into the holder. I may replace that. It's a 1/16 of an amp fuse. From the construction, it looks like it's slow blow, which would make sense for the inductive load of the power transformer, small as it is. And I'm going to undo this jury-rigged, brittle, solid core wire that the previous owner had put in there and replace it with the good stuff. Get rid of this fuse holder, and I'm going to yank that fuse holder as well, which I'm pretty sure is in the yeah, there's a foil that was blown there. You can see where it blew off the board, and the guy had just jumpered up to that fuse. That's going away back to original state, and the only evidence that this fuse has been added is this one little screw hit on the back, which I think is not too bad, a compromise. There's really not much else to this now except to get it up on the workbench, get it out of the shop and up to the laboratory workbench, and see if the circuit's fried in some way. Oh no, I'm sorry, there is more stuff. I have to recap this thing. There's that step. I need to get busy and order the parts, because I forgot all about that. So that's the next step. And I got word that the bolts I'd ordered shipped today, so those will be coming in, so I can get the nice stainless steel bolts on here instead of all the rusty corroded ones. So progress is being made. Okay, a little bit of history about this meter. Looking in Chuck Penson's complete book of Heathkit test equipment products, I find here the IM-25. Says it was introduced in 1967 and continued through 1974 at a cost of about $80, which most of the online inflation calculators say that's roughly $620 in today's money, $20 that is. That's unrealistic, of course. Those are usually based more on, what does buying power equate to, your income relative to how much stuff you can buy for it, but there are all these other variables in that which don't just apply to the cost of a static item. So that number I think is unrealistically high, but still, for purposes of comparison, it's a fairly pricey meter. There's a pretty good paragraph on it here. He even exclaims that it takes a mercury cell, it takes 2 C cells for the, or 2 C batteries for the ohms range, and then 14 more C cells for the rest of the meter if you're not running it on AC power. And it's probably rightly ridiculed here because there's other ways of dealing with that, but the way Heathkit designed this meter, if you want isolation from the line, you need to use the battery power. So it's a little bit funky in that regard. Still, it was successful enough that they made it for, what was that, 4, 5, 6 or 7 years. So in this 1967 catalog, in the VTVMs section, they have this classic, which was made under several different model numbers and improved styling, but basically the same meter. That's stalwart they had for a long time. And then they have this product here, which is a little nicer. It's still a vacuum tube voltmeter. And then another, as they say, AC vacuum tube voltmeter for accurate AC measurements. And then a standard volt ohm meter, and that's it. Those were their meter offerings in 1967. And even if I go to the winter catalog, which might have had some late additions, of course I don't know if that means this is the winter that came before the general catalog or the winter that followed the general catalog. I'm not sure which one of these is actually earlier. Here's the fairly brief test equipment section. They have the same volt ohm meter and the same other 3 meters. That's their whole meter lineup. The AC vacuum tube voltmeter, the regular vacuum tube voltmeter, this version of the vacuum tube voltmeter, and that's their whole meter lineup. So jumping ahead to the next catalog I have in my collection, which is 1970s general catalog. Let's see, a lot more stuff. We have the restyled AC and DC meters, and the portable version, and the same old VOM. And here we find the IM-25 kit, $94. And again, the inflation calculator puts that at about 620 some odd dollars. It's a nice looking meter. It has a lot of nice features, such as the ability to have separate selections, range selections that is, for each of the things that it's measuring, volts, ohms, and amps. And so if you're going back and forth between several different types of measurement, you're not constantly racking the range switch around. You just leave it for the appropriate range for each type of measurement, and then just change the one volts, ohms, amps switch, which is a nice feature. I wish more meters had that. And it has a really nice large meter on it. And even though it's sort of an odd duck in many ways and has its own design flaws, still it obviously ranked quite a good mention in their catalog. And the price commands a more discerning buyer, I guess you could say, or a more serious buyer if nothing else. This mess here needs to be fixed, along with my revisions to put the fuse in and so on. This makes it really hard to work on, and if you're not careful, you yank on these and it peels the foils off the board. This needs to be remedied. And I've purchased some Molex connectors that I'm going to put in line, so during work on this thing, this back panel can be disassociated from the main body. That should make it a lot easier to work on. Alright, a lot of the foils were peeled off where these wires go through, so they couldn't just be stuck in the normal way. They were kludged together pretty horribly. So I've got... they originally didn't make any differentiation between hot and neutral, but I've still identified neutral as there and hot as here. Trying to put the fuse on the hot side. Goes through there, and then I've put in new wiring. Instead of the solid wire that was there, I've got stranded wire, and it's twisted and feeds through a new hole I drilled in the board, at which point it comes over and then goes into the holes from the component side, as it should, and is soldered down there. However, the pads were torn off, so I had to scrape the silk screen off the board, bend the leads over, and then solder them. I'm going to secure this with some epoxy and or hot melt glue to make sure those don't lift and there's a strain relief. Similarly, I had to put the battery wires into holes and then bend them around coming from the proper side of the board. I've got the leads twisted, drilled the holes. This shouldn't have been like that, it should be like this. And the black leads were both torn out, so they're bent over and soldered along the foils, but the red leads were okay and they go into their respective holes. So now that I've got the lay of the wires figured out, I can see where I want to put my Molex connectors. Probably right about here, and similarly about at the same point on all the wires. And I guess I'll do that before I secure these. The male parts of the Molex connectors are, there's the Molex part number and the DigiKey part number. I've got 3 of those. And then the corresponding female Molex connectors. There's their Molex number and their DigiKey number. I have 4 different types of Molex pins here that go in those connectors. There's the one that's a socket, the female part, that's for 16 to 18 gauge wire. And then there's the comparable part for 20 to 22 gauge wire. And that again is the socket, so it's probably easiest to see those here. This one they're just wrapped up in a roll, but it's the same thing, just a slightly different size. And then the pins, this is the 20 to 22 gauge wire. Again, they're the male part. And then here's the corresponding one for 16 to 18 gauge. I don't think it really matters whether the male and female pins go in the male and female connectors, or if you can have male pins in the female connectors and vice versa. I think it'll work either way, but I want to check with the Molex catalog real quickly before I start assembling these. I've decided to make this the female side, and since the battery power and the AC power all come from the back panel, they're the source and they're going to have the male connectors, and then it's going to go that way and the female connectors will be here. I've also decided to use the female pins or the female contacts with the female connectors. Now these are really supposed to be put on with a crimping tool. That's quite expensive. I don't know, it's hundreds of dollars anyway. And I don't have the quantity of these things that makes it worthwhile spending the money on the tool, so I just carefully bend them over with a needle nose pliers and put a tiny sweat of solder onto them to hold them in place, because the crimps aren't tight enough the way I do them to actually hold the wire in. And then everything else is just bending the tabs over enough that they fit into the housing. Now I have to do, these are the ones that are rated for 18 gauge wire, so this is I don't know, like 20 gauge wire or 22 gauge wire, so I'm going to use the smaller pins on those. So those are on. Now I just have to do the other ends of the wires. So there are the male connectors, and I have to put something on this so I can keep track of which one is which without having to trace the wires back. Okay, 1 to 1, 2 to 2, 3 to 3. I think that's a big improvement. Wish Heathkit had done something like that originally. Or really, they could have put connectors right on the board here and just had the wires plug into them, even if they're screw terminals. Okay, I've got the restored ohms battery socket bolted onto the circuit board now. And here's my battery. And I have to remember that the case is positive, which is opposite from most batteries of this general style. I have marked the terminals plus and minus. but it's two-hander to get it in there. Like that. And so that socket is now wired up. Well, not a beautiful job of hot melt glue. There's another one. It's not exactly a precision applicator. Now I want to decide if I want to put any epoxy on these, and I'm thinking no, because if it turns out I have to redo these joints for some reason, it'll be really hard to get the epoxy off. So the next step is to replace the electrolytic capacitors. So there's the main electrolytic capacitor, which my camera doesn't want to focus on. It's a 250 microfarad, 25 volt. No great demands there, but I wanted something with the same form factor, and I was just having a heck of a time finding anything. And then finally one of the application engineers at DigiKey conjured up this part, which is a Vichy Sprague part. There's their number TVA 1312 E3, and it's a 250 mic 50 volt axial, close to the original size, so that's what I expect I will use. A Sprague Atom capacitor. 250 mics, 50 volts. I think I want to look this up in case there's something weird about this part. I mean, it should work in this application, but I still want to see if there's some odd specification to it. All the other electrolytics are the same kind. They're all what are they? 10 microfarads at 35 volts. 4 of them, and I had those in my parts bin. Very close to the ones that are in there originally, except in color. So it turns out this is a fairly normal electrolytic capacitor. Its major claim to fame is that it's a low leakage type. So, you know, somewhat of a premium capacitor, but otherwise nothing too exotic about it. It's listed by Sprague as being a general purpose filter capacitor. Good for power supplies and things like that, which is exactly how I'm going to use it. So there's that cap installed. And this is a probe maker on eBay I've used before for my vacuum tube voltmeter probe. Kent Craft for the IM series VTVMs and the IM-16 and IM-25 solid-state VTVMs, or FET voltmeters, or VOMs. 1 megohm resistor installed in DC probe. Alright, let's look at the front panel of the meter. I always liked the concept of this meter, just not very much the implementation. It's a large meter. It takes up quite a bit of room on the bench for what it does. Function-wise, it's really a fairly pedestrian volt, milliamps, ohm meter. But we do have a very large and attractive meter movement here with several scales on it, color-coded, but not color-coded to the front panel the way Heathkit did on some other equipment. In other words, the silk screening here doesn't necessarily correspond to the colors over here. We have a total of 7 controls, 6 knobs, and a thumb wheel knob. You've got the power supply switch, which is off, powered by the line voltage, meaning the AC power line, or off of batteries. And it's a bit of a misnomer because to use it in all functions you still need to have some batteries in it as it's originally designed. Line just removes the main battery pack from the equation and replaces that with the internal AC powered power supply, but you still need to have the other battery pack and the special 1.3 volt mercury cell in order to use the ohms function, even while in the line position. You have the basic function selector switch, volts, ohms, and milliamps. And as I've mentioned elsewhere, Heathkit they weren't really following the normal engineering conventions. I don't know if that's because they thought the target audience for this wasn't into the whole upper-lower case metric nomenclature standards, or if they just thought it looked better this way. I don't know, but this means mega amps. It should have been a lowercase m. Anyway, it means milliamps here. And then above in the same pattern is the range switch for volts, the range switch for ohms, and the range switch for milliamps. Then finally you have the AC-DC switch, and the DC has a polarity minus and a polarity plus position, which is always handy if you've got your leads connected contrary to the polarity of the circuit. You don't have to redo your test leads, you can just throw the switch. There are a different number of range positions for each of the functions. The volts function has 9 positions, from 0.15 volts full scale to 1500 volts full scale. The ohms function has 7 range positions, which are multipliers, not full scale. So you take whatever's on the meter and multiply it by 1, by 10, 100, 1000, 10,000, 100,000, or 1 megohms. And then finally the milliamps function has 11 range positions, from 0.015 milliamps full scale up through 1500 milliamps full scale. Other than the 7 controls here and the meter, there's also a power on neon bulb, which only works if you're in the line power mode. It is not an indication of power if you're running on batteries. Now here's an interesting thing. I've never seen this on a meter before, but notice on the milliamps function, the range switch has 2 sets of numbers. The bold numbers represent the amount of milliamps that will cause a full-scale deflection of the meter. So that's very normal, typical. The smaller numbers represent the amount of resistance that the meter current shunt adds to the circuit for each of the ranges. So, for example, if I'm in the 50 milliamp full scale range, it's telling me that the meter is adding 3.16 ohms to the circuit. And since milliamps must be done by putting the meter in series with the circuit under test, sometimes it's important to know that, hey, I'm adding 3.16 ohms into that circuit. It's kind of like Heisenberg, right? By measuring something, you change it. So how accurate is your actual measurement? Most meters just don't even bother telling you that kind of thing. There's always a shunt, but in most cases they just assume that the shunt is of a value that's so small as to be unimportant or negligible, but in this case they spell it out for you. If you're way down to the 0.015 milliamps, that's a really small value. This is actually adding 10 kiloohms of resistance to the circuit. But again, if you're reading such small amps values, probably the circuit you're reading has very high impedances in it, and maybe 10K is negligible in that context. Anyway, it's an odd thing. I have never seen that before on any multimeter, really. looking at more detail on the meter, there's one scale for ohms, and that's in green. So whatever you get here is going to be multiplied by the multiplier on the range switch. And notice that it's a non-linear scale. You start up here with 1 and you go up and everything gets more crowded, and pretty soon you're up to 1000 on the meter, and 500 is only right here. And there's a reason for that. It's the unusual way that Heathkit designed the ohms reading circuit, where the resistor under test is actually being put in parallel with an internal low resistance, I believe it's 10 ohms resistor, which has a regulated or constant current going through it, because what the meter is really doing is it's putting the resistor under test in parallel with the internal resistance and then measuring the voltage drop across that. And because the internal resistance is always 10 ohms, you're going to get a non-linear response on the meter. So I personally hate that. I don't know why they did it that way. It seems like just a bad idea. But it's not like you have to really work up in this part of the scale. You can change amongst the many ranges on the ohms function to keep the readings more down in this part where the scale is spread out more. The volts function and the milliamps function have their ranges alternating between a 15 and a 5 full scale. So 0.15, then 5, then 1.5, then 5, or 0.5 here rather, and going on up, and the same thing for milliamps. And so accordingly, the primary DC volts scale has a scale going up to 15 and another one going up to 50. And by the same token, if you're measuring RMS AC volts, you have a scale going to 15 and another one going to 50. And you just pick whichever scale corresponds to the class of range, whether it's a 1/5 full scale or whether it's a 5 full scale. And then we have this oddball dual scale stuck in the middle, and that has 0 as its center, and then it goes to 7.5 one way and 7.5 the other way. That's supposed to be half of the 15 scale, so it's plus or minus half of 15. The other one goes minus 25, 0, plus 25, and that's supposed to be half of the 50 volt scale. So that's an unusual feature of this meter, that using the 0 control here, you can set 0 as being here instead of here, and then that allows you to measure positive or negative DC volts or DC milliamps without having to flick the switch here. And the manual points out that sometimes when you're doing certain types of measurements, you don't know what the polarity is going to be, and the polarity may be constantly changing, even if it's not really an AC signal. It could be used for nulling out certain circuits and things like that, where you may skew into the negative side and then you do some adjustments and it goes back positive, and it's impractical to keep swapping the leads. So that's a pretty cute function Heathkit put in this meter. Probably most people would never use it, but it's here, and it's either the, well, I wouldn't say the only Heathkit that had this feature, because I haven't looked at every model, but of the ones I have looked at, it's unique so far. And that drove me nuts calibrating this, because the manual did not say which scale it was talking about when you're doing all the calibrations. It would just say, adjust to 6.5 on the meter or something. Okay, well, adjusting to 6.5 here is not the same as adjusting to 6.5 here, which is almost full scale one way or the other. And I kept thinking it meant this one, and it meant the regular one. Okay, let's do a little bit of a demonstration. Right now I only have the AC power plug as I modified it. So this assembly is AC powered, but I don't have any of the batteries connected at this time. Well, I'm sorry, I do too. I have the 3-volt battery connected up because I'm going to be doing an ohms demonstration, and I don't have my battery eliminator completed yet, so I'm still going to run this off of batteries for the ohms. But I don't have the 1.35 volt mercury cell, and as it turned out, I cannot use the 1.5 volt alkaline replacement cell. The voltage is too high and I cannot adjust that out of the circuit. So when I get to the ohms part of this demonstration, I'm going to hook up a bench power supply set to 1.3 volts with jumper leads just going over to the battery clip to simulate that mercury cell. So I have my modern test leads plugged in. It has the common alligator clip, and then it has the 2 probes. For AC volts or AC amps or ohms, you use this probe, and as it says, it's directly connected, so the wire goes directly to the probe tip. For reading DC values, whether it's volts or milliamps, the red probe is used, and that adds a 1 mega ohm resistor in series, and that's internal to the probe handle here. So it's between the test lead and the probe point here. And I'm still not used to doing that, even though my vacuum tube voltmeters, including that Heathkit one, which I have a video on, do the same thing, but it's still not something I deal with otherwise. And I got a few times when I was getting really squirrely readings, like when I was trying to test ohms for initially. I was using the DC probes. I thought, well, the ohms are DC, and everything was way off because I was adding an extra 1 meg ohm resistor in series with the resistor under test. Okay, I have the alligator clip common and the DC probe connected up to one output of my bench power supply. I'm going to turn the meter on, and I have to use the 0 thumb wheel to null the circuit out. Okay, I'm going to start out in the 5 volt range. My power supply is set to 0 volts. I'm going to turn it on, and of course I get a 0 reading here. Now if I go up to 1 volt, well, I stupidly had it in the ohms mode, so now it's in the volts mode, and I'm on the 5 volt range. I've got 0 volts here. Power supply is on 0 volts. Since I'm in the 5 volt range, I should be looking at this scale, which is calibrated to 50, so everything I read here is going to be 1/10 of what it really is. So I'm going to go up to 1 volt. Right, so it's reading 10, but it means 1 because it's on the 50 volt scale, but it's only a 5 volt range. So there's 4, and it's right on the money. I can go to 4.3, and it's pretty much dead nuts on. And now I can go up to 5 volts. And now let's go up to the 15 volt scale, or the 15 volt range. So now I'm going to read off of this one, and it's reading 5 on that scale, so that's correct. I'll go up to 12 volts. Oh, that's 11 volts, I'm sorry. 12 volts. It's just a hair high. So I've overranged it here when I give it 19 volts. I'm going to go up to the 50 volt range. So I'm reading just a hair above 19 on the scale here. And my power supply maxes out at 32 volts, and it's reading just about more like 32.5 volts here. That's well within the specifications of the meter. Going to take it back down to 24 volts. So again, we're just slightly high of 24 on the scale. So the DC volts works. Okay, I've switched over to the milliamps function, and I've selected the 50 milliamp range. The meter is approximately zeroed. I have to tweak it a little bit. There we go. It had gone a little bit high, which probably accounts for part of the reason why the readings were a little bit high on the voltage part of the demonstration. I should have re-zeroed it before I did that. So I have, as I usually do on these Heathkit meter videos, when I'm testing milliamps, the easiest thing I have to test them with is my home-built 4 to 20 milliamp current loop tester. And I have the power supply set to 24 volts. The tester and the meter are connected in series and then placed across the 24 volt power supply. So make sure again I've got everything selected correctly. I'm going to turn the power supply on, and it does not work. Why does it not work? Well, I'm trying to measure milliamps here, and I've got this probe that has an internal 1 mega ohm resistor, which is way too high for a current loop. Okay, I just swapped out for the direct wired probe. I've got an indication here of loop current. I'm looking on the 50 volt scale, and I've got a reading of 12. 12 is the halfway point between 4 milliamps and 20 milliamps, and the knob here is centered, so I should be getting 12 milliamps, and that's what I'm getting. If I throw this switch here, it should go to 4 milliamps, and it does, right on the money. Relieve the switch, it should go back to 12. Throw the other switch, and it should go to about 20 milliamps, which it does. Take the switch back, goes to 12 milliamps, and now I can turn the knob around. So that's just a basic demonstration that the milliamps function works on here. I'm not going to try to demonstrate it in every possible range. And I think the issue is caused here by some mismarking on these probes by the maker of these reproduction probes. It does say AC and ohms, and this one says DC. It doesn't mention volts or current though, and I think the reason for that is that these are primarily made for use with vacuum tube volt ohm meters, which only measure voltage and resistance. They were not designed or marked for meters that can also measure current, in which case even if the signal is DC, you don't want to have a large value resistance in series when you're trying to measure the current, because that'll throw everything else off in the circuit under test. So I may actually, since the maker of these probes is listing them now on his website or his web store on eBay as being useful for the IM-25 and the slightly lesser model, which the IM-18 or something. I have to double check. I don't remember the model number offhand. But he says they're useful for that, but he might want to do something to say, you know, if you're measuring milliamps, then use the black lead. Just a little change on his label, perhaps. Okay, I'm going to do some AC voltage now. I've got the meter in the volts function. Since I'm going to be measuring line voltages, I've got it in the 150 volt range. And I'm using the direct probe, which is good for AC. And it's connected through my benchtop AC access box, which I have a YouTube video on. And that's plugged and turned into my variac, which is set to minimum. And I'm going to throw the switch here. And as expected, I should see nothing on the meter at this point. Since I'm on the 150 volt range, I should be using this upper scale. Now if I go up to about 50 volts on the variac, oh yeah, my mistake. That's for DC. AC needs to be read down here. So the 15 or the 150 volt range needs to be read on the red 15 scale for AC. And if you account for parallax, looking at it correctly, it's just a hair under 50 volts. And the variac meter is a little off, so I'm going to crank it up to where I know it's usually closer to 50. And indeed, it's right on here. So I'm going to go up here to 100, thereabouts. And it is very close to 100 here. And then up around 140. It's actually a little higher. It's more like 145 according to this. So AC volts works. Okay, for ohms, I have the meter in the ohms function. And just to start out on the lowest range, I've got the ×1 multiplier. So whatever's on the meter scale should be the actual value in ohms, starting at the low end. The meter is zeroed out. I've got the meter connected with its black AC and ohms probe and the common stuck into my Heathkit decade resistance box. And I'm going to crank her up to and I should mention that I've had to clip on a couple of test leads to the mercury battery holder. And those are going over to the secondary channel on my power supply, which I've got set to 1.35 volts. I'm going to turn that guy on. So now the constant current source in the meter should be working. And want to make sure everything's zeroed out here. Adjust this guy for 0. And go back into my ×1 range. Zero the meter out. And now if I go up to, say, 4 ohms, I've got 4 ohms here. Well, a little bit shy of 4 ohms actually. Oh yeah, that's because I had quiescent resistance in here. I tried to dial out the quiescent resistance, but that skewed things a little bit. There should be about maybe half of an ohm of quiescent resistance in the circuit, so I'll have that in there. And now when I go to 4 ohms here, it's a lot closer. So let me just say that is 4 volts. There, okay. If I go to 7 volts, I'm right up to 7 on the meter. If I bring in 10 ohms down here, it's a little bit off up here, but that's about 17 volts, which, you know, very close to 17 volts, depending how you read the meter, the parallax issue. So 17 volts is, or 17 ohms rather, is what I would expect, because I've got 10 ohms here and 7 ohms here. So now let me go to the next range. I'll go up to the times 10, and so 15 is halfway between 10 and 20 there, and I'm a little bit higher, so 17 ohms is still reading correctly on the times 10 scale. Let me take that lowest guy down, and let's take it up to 50 ohms. So I'm just shy of the 5 mark here, and that is what it should be for 50 ohms. Let's bring up 300 ohms here, so it should be around 350 ohms. And there's no 40 on here, so this tick mark here by my fingernail is 40, so it's halfway between 30 and 40, and that's what it should be when it's set to 35 or 350 ohms. So that's reading right on the money. Let's take it up to the times 1K. I'll take these low range guys down. I'll go up to 3K on here, and it's reading just a little bit low on here, but it's pretty good. And actually, let me just make sure the meter is correctly zeroed again. It's reading a little bit low, so I'm going to bring it up like that. And it does read infinity when the probes are opened, as you would expect an ohm meter to do. Now I reconnect it, and now I'm giving it 3K, and it's right on the money. So re-zeroing it helped. Let's go to 8K. That's where we're at. Let's take it up to the 10K multiplier, and it's considering that this is supposed to be 10K down there, 8K is right about where it is. Let's take it to 78K, but now we're in a part of the range where it's kind of hard to see exactly where we're at. It's too much. Well, no, I could be in the times 1 range, but even then it's like, okay, that's 50 and that's 100, everything's bunched together there. It's hard to tell what the value is. If I go to the 10K, well, it looks like it should be 80K there, but in fact it's more like 78K. So you can't differentiate with this meter very well, no matter which range it's in, because of the way things are bunched up here. You're always going to be a little uncertain of what your reading is. Anyway, so let me put it up in the times 100K range, and I'm going to give it 600K, and in that case it's right on the money here. So the ohms range is working perfectly on this, or at least as good as can be expected given its design. Because I don't have any convenient way of doing a lot of testing with AC amps, I'm just going to do what I do with my other, I mean, I can hook up an AC power supply, but all I really have is my variac for that, and I don't want to put anything AC powered into my one and only resistance decade box, which isn't really set up to be used that way. And I don't have a bunch of power resistors or anything laying around that I can easily rig up a circuit for that. So all the circuit modules have already been tested. The AC processing circuit obviously worked because it was used for measuring AC volts. It would also be used for measuring, I think it gets used for measuring AC amps too, but maybe not. There's something weird about that. I'll cover that when I talk about the circuit theory. Anyway, I've certainly checked every module of the circuit here and everything is working. So the remaining thing to do is to try it out in the zero center mode. So I've got my meters, again the red DC volts test lead connected up to my bench power supply, which is currently set to 0, and it's turned on. I have to go to DC plus. It says in the manual that if you're going to be using the zero center mode of the meter, you must be in DC plus. So I should be able to, rolling the thumb wheel here, quite a bit of rolling, bring it up to 0 here, and I'm still in the 50 volt range here. So I'm going to turn my power supply, it actually is on already. I'm going to go up to 12 volts, and so half of 50 is 25, so I should be here on this scale, and there's 10 volts and there's 12 volts, so I'm right on the money. Now if I swap my test leads, now the meter swings down here to minus 12 here. So that's working just fine. Let's go up to 24 volts. Minus 24 volts, it's right on the money. And the same thing over here, minus 24 volts on this side when I put the test leads back to the way they were. So that function works. So I'm going to roll what the meter thinks is 0 back to 0 over here. And I'm going to connect up my test leads again. I've applied minus 24 volts and it's pegged because I hooked it up with the wrong polarity. Here's where I can use the reversal switch. And on the 50 volt scale, 50 volt range, 50 volt scale, I'm reading about just a little over 24 volts on the meter. And I should try turning that off. Yeah, I might be a little bit high on my zeroing here, so re-zero it. Reapply the power. Yeah, now I'm right on 24 volts. One of the things this meter is notorious for, just looking at various forums and written histories of it, is that it's not a very stable circuit. It's necessary to zero it a lot, which is really annoying if you're used to more modern meters or just really better designed meters. In spite of the nice ergonomics of this, there's some really strange stuff that Heathkit did, not the least of which is the massive number of batteries it requires for operation, and just some strange design decisions they made. It's just not the most stable thing ever conceived. Just a reminder here before I forget to mention it somewhere else, is that according to the manual, and I did notice this during my circuit study, only something like 0.07 volts, and I'll confirm that amount, yeah, well, 70 millivolts or less, that's the voltage that's applied to the resistor under test, and that's not enough to forward bias a diode, not even a germanium one. So as they point out here, this meter is not suitable for testing diodes. And they also mention that the battery is constantly consumed while you're in the ohms position, even if the power is turned off. So you should never leave the meter in the ohms position for extended periods of time. You want to see what failure looks like? there's failure and a lot of dust. When I was restoring this meter after the physical restoration I've already shown earlier in the video, when I was actually trying to get the meter working electrically, it was just pretty much deader than a doornail. All it would do is peg the meter, and tests of the power supply and so on were indicating that everything was good, so I was going through and making sure the switches were making good contacts and that there were no opens on the circuit board foils and obvious things like that, and nothing was working. So it was not clear to me, and Heathkit's troubleshooting manual steps didn't really help in this situation, except to cast the blame on transistor Q7 for a lot of woes. And as I was studying the circuit, I was able to make more sense of which transistors were doing which jobs. And it's like, well, no, if this has failed, even if it's failed short or failed open, that wouldn't cause this, and going on. And is this problem common to all functions or just certain functions? That kind of analysis. And I came down to the realization that almost for sure the transistor known as Q7, which is a JFET, it's the main buffer amplifier in the meter circuit. Everything has to go through that, and if that's not doing its job, then nothing's going to work. And so I looked it up and found out that it's a part that's no longer produced. And apparently somebody had tried to fix this before, because when I checked it, it did not have the same FET in it. I'm looking through the viewfinder of my camera here. I can't even pick up a transistor. This guy here was some other FET. It was not the one Heathkit provided, I think. So I think somebody else had tried to fix this at some point and put in a different JFET. And I looked it up, and this is a general purpose JFET, but it didn't really have the same characteristics as the original. So I hunted around, and Quest Electronics in California had exactly 6 of these things in stock, in the original package anyway. Instead of this package, well, come on camera. Maybe I should unzoom it, huh? Maybe that would help. Yeah, in this package, it's this little dome top plastic ceramic package. Very obsolete looking. And that's what the Heathkit manual said. It's a 2N4304. And like I said, I got it from Quest Components, it's called here. I said Quest Electronics earlier. And like I said, their website showed exactly 6 of these things in the original package that Heathkit called for, and just for authenticity I bought that entire stock, because there are 2 such transistors in this meter, and I was already pretty sure that one of them was bad, and maybe the other one was too, and I have 2 more of these meters in the pipeline to be restored, and if those have the same problem, I'm going to need all 6 FETs. So I decided to buy those. They did have a fair number of other ones with the same part number but in a different packaging, which I could have bought. Anyway, as it turned out, this particular meter only had this one FET, and it was bad. Or if not bad, it was just because whoever substituted this one for the original put in a part that had different characteristics. And so one way or the other, it was not allowing me to balance the circuit, although it did get it to the point where it wasn't pegging the meter anymore. So I had read that this meter is incredibly susceptible to RF fields, and not in a way where it just reads incorrectly if you have a strong RF field around, but to the point where it fries internal components. And you know, you're not picturing it blowing up power resistors or wire wound resistors or something, it's most likely popping the semiconductors. And my guess is that's why somebody before had tried to fix this meter and just grabbed some FET they had on hand. As soon as I put the correct kind in, it was much better, but it was still out, and that Q7 FET is in a circuit with a constant current regulator transistor, which is just a normal NPN bipolar transistor. And I bought from Mauser Electronics a bag of those things. They had tons of these available. And just by a process of elimination and diagnostics, I determined that a total of 4 of those in this circuit were dead. One of them in the buffer circuit along with the FET, and that definitely fixed that problem. And then as I was going through the different functions on the meter, I found some more transistors that were not quite right. There's a temperature compensation circuit, which this thing was very drifty, and I thought, yeah, that temperature compensation circuit, if that's not stable, then it basically, that circuit is the common return for the whole bipolar meter drive circuit. So if that is not regulating well, then the meter's just going to drift all over. So I did replace all 3 transistors in that circuit. It's the same model of transistor. All of the bipolars are the same model, which is convenient. So if anybody else is trying to get one of these old horses working, I would strongly suspect that if they're not, you're going to be looking at changing out at least one FET and possibly some bipolars. So in case I forget to mention it during the circuit theory part of this video, this is the area where the transistors fried or were partially damaged. This is the buffer amplifier. All signals come in from their front end range switching circuitry, and they're all applied to the gate of this 2N3404 FET, and that works in conjunction with this current regulator based on a 2N3393. That's an NPN bipolar transistor. And the two of them work in conjunction to act as the buffer. And if this isn't working right, if this one isn't working right, you're just going to peg the meter. There's no control over the signal going to everything downstream. And its tendency seems to be to peg the meter, just to go to severe overrange. If you get this one working, as I did, and it's still not reading correctly, although it's starting to respond and you can't really calibrate it or dial it in, this is the one I found that was the culprit. So replacing these two things here brought this meter back to life. And then I checked all these transistors. I was prepared to have to replace these two, but these are in sort of a more robust, protected part of the circuit, and they were fine. And everything comes off the positive battery rail, goes through all this junk, and ends up coming out. This is a balanced circuit, and that allows for the plus and minus meter reading. And then all the current coming out of that comes out this one common point and goes through a current regulator here. It's basically a constant current sink with two transistors providing the reference voltage to it, but they're connected in a way that causes them to also act as a temperature compensation element. And these are the three transistors I had to replace to keep this thing from being so drifty. So again, if anybody else is trying to restore one of these things, these two guys and these three guys were the biggest culprits. These two transistors are used as diodes, and they're just in the over voltage protection circuit. Those were fine. And then up here, there's two more used as diodes. This is in the AC attenuator circuit. Those were fine. And the FET in the AC attenuator circuit was also apparently fine. I did not need to change that. And then there's also one more bipolar down here in the ohms constant current mode, or constant current circuit, which was also fine. Alright, let's take a quick look through the Heathkit manual for this IM-25. This version of the manual was published in 1969. As the manuals did in those days, they had an inside cover with component identification illustrations, table of contents, introduction. The Heathkit model IM-25 solid-state VOM, or volt ohm meter, combines all the features of a vacuum tube voltmeter and a volt ohm milliammeter into one attractively styled cabinet. Operation from a 120 volt AC line or from internal battery is selected by a single switch. The self-contained battery supply allows you to perform all measurement functions at remote locations without an AC power source. A separate range switch is provided for each of the three functions: volts, ohms, and milliamperes. This makes it possible for each function to have a different number of ranges. I would think it would be more significant, actually, that it allows you to keep each type of function having its own range set and then go back and forth between them without racking a range switch around, but okay. Readings are displayed on the large 6-inch meter, which has 3 separate sets of scales. Each set of scales is a different color. For example, all AC voltages are in red scales, etc. Additional features of the solid-state VOM include a low voltage ohm meter for accurate in-circuit resistance measurement in transistor circuits, a circuit board and cable assembly for clean or easy and clean construction, a single test probe to eliminate tangled test leads, and a dual winding power transformer that allows you to wire the voltmeter to operate from either 120 or 240 volt AC power source. Whoever built this kit, and this manual did not come with the kit that I'm showing in this video, it was something I purchased separately on eBay. This guy just marked the heck out of his. He was crossing stuff out, and like, I guess I'm done with the resistors, so cross out the word resistors. All sorts of things. He's a real marking nut. There's another component identification pictorial specific to the kit. And then the step-by-step assembly of the circuit board. As usual, Heathkit would show the entire board, then they would gray out or highlight a portion of the board, and then that portion would be shown enlarged. Here again, this fellow or person also colored in all the components as he installed them, so more than necessary probably, but it's his manual. And we work on the bottom part of the board around the switches, and then back up in the upper corner and lower corner there's a brake section there to install all the transistors, installing the power transformer and the wiring harness. And this person colored in the colored wires with colored pencil. Mounting various components directly on the selector switches. Mounting the selector switches to the circuit board. And the sub panel, which has all the calibration pots on it. Wiring up the switches to devices on the sub panel. more information on mounting and identifying things on the subpanels and on the switches. Point-to-point wiring between subpanel and switch devices. All of the step-by-step instructions that go with those illustrations, those are folded out so you can see those and this at the same time. Assembly of the circuit board and the subpanel and the front panel and the bezel with all the nuts and spacers and so on. Building up the battery holders, mounting the battery holders to the rear panel, hooking up the power cord, wiring up the battery holders to the circuit board, wiring the meter, and they have an illustration here about putting the knobs on and actually mounting the meter. So apparently that is looked at before you do this part of it. Instructions on how to mount the inserts into the knobs, how to assemble and wire up the probe, more of the same. And there was also apparently some sort of a test probe. I'm not sure what they're saying there. Looks like there was some short test probe that was separate from the main probe. Then the calibration instructions, which aren't all that extensive really. They show you the things that are on the sub panel which need to be adjusted. DC calibration, AC calibration, including AC bias control. And there's 2 or 3 different methods for doing that depending on if you have no other test equipment, or if you've got another meter, or if you've got so on. There's different levels of adjustment. Frequency compensating trimmer capacitor adjustment if you have an oscilloscope and a signal generator. Otherwise you just set them to X number of turns from one extreme of the turn and hope for the best. Illustration of what everything on the front panel does. This is continuing the AC calibration, and then ohms calibration, final assembly, putting on the case top and bottom, the feet, and then 1, 2, 3, 4, 5 pages of operation instructions in case of difficulty section with some troubleshooting charts, maintenance, additional accessory probes you could purchase, specifications, more specifications, the circuit description, and some diagrams showing only pertinent parts of the schematic broken out. More circuit description. And again, a sub-circuit broken out. And another one. And another one. And another one. More circuit description, another breakout diagram, more fold-outs, another sub-circuit diagram, the circuit board X-ray view, some chassis photographs, and then replacement parts list, which also has prices on it. Functional parts list. This is unusual in Heathkit manuals. I've not seen this before, actually, to the best of my recollection. It goes through practically every resistor, capacitor, transistor, and tells what its job is in the overall circuit. And then we're done. And there are also a few pages here in this 3-pane fold-out, which got separated from the binding. So they're just additional illustrations. Okay, here's the schematic diagram. I'm going to give an overview on here. Then, as usual on these videos, I'm going to present a series of sketches of subcircuits redrawn to be clearer and easier to understand. So this has got to be one of the most confusing Heathkit schematics I've ever encountered, and it stymied me. This project's been going on for about 2 years, and I initially had so much trouble reading parts of this schematic. I had not yet taken the time to really do detailed circuit study, and I had not redrawn the schematics to make sense. Just untangle this web, basically. Only when I did that did parts of the circuit start to gel, and I started understanding what the approach was Heathkit's engineers took in designing this. And then things started to click, and I could see, oh, I see where the problem probably is, that type of thing. But they show the input probe here. If it's in AC or ohms or milliamp position, then it's a direct probe through an internal switch on the probe. But if you're in DC, then it goes through a 1 megohm resistor. And this is not terribly clear because you need to have the switch in this position for milliamps, whether they're AC or DC, and of course in ohms. So the AC really applies to AC volts. It's not very clear from this. But if you start trying to measure milliamps and you have the switch in the wrong position, like down here because you think, well, it's DC milliamps, then you're going to get some weird results because of this resistor. It depends on the circuit you're measuring. Some circuits maybe wouldn't be that greatly influenced by it. You've got the 1/4 inch tip sleeve type phone plug and jack, which was popular in those days for meters and so on. There's a sub-circuit for the AC attenuator, which is used instead of the main attenuator when you're in AC volts, at least. Yeah, and it has to be, you can see here that you come in through the input jack, and if you're in volts and if you're in AC, then the signal goes through here. But if you're in milliamps, it goes through its own attenuator, well, not attenuator, but shunt circuit down here. And let's see, does it ever get back? So we develop a voltage across here, we come back, we're in milliamps, so it doesn't go this way. Yeah, if you're in milliamps, it bypasses this circuit. So AC milliamps does not use the AC attenuator circuit. It's voltage only. And then you've got this big long voltage divider, which is also used as the part of it's used as the current shunts for the milliamp ranges. And there's also a reference resistor that's built out of these, but only in the ohms mode. Here's this confusing circuit made worse by whoever marked the heck out of this here and crossed things out and wrote over it. This will be probably clearer in my redrawn sketch. Somebody was trying to do a battery eliminator for the mercury cell here in a way that I'm not positive will work properly. I did see on a forum where somebody was talking about something either just like this or nearly like this, and they said, well, it gets the ohms range working, but the accuracy is poor. And that's kind of what I thought. I thought because of the way this works in the two parts of this circuit, one's influencing the other, and it's like, yeah, I don't think that's going to work all that great. You'll get some sort of a readout or a meter displacement, but it probably won't be quite what it should be. Anyway, so more range switches all around here, more switches for the functions and the routing of signals, protection transistors. This is a constant current sink that's common to the whole meter drive circuit. This is the meter drive circuit here. It's a differential circuit, and the various switchings of the meter in the different functions and the different positions of the DC plus, DC minus, and AC selector switch, and then all the calibrate controls on the sub panel are here. Diode bridge, the differential transistor stage is here, and then the heart of the whole thing, which is the high impedance voltage follower circuit. Essentially, it converts from this circuit to this circuit, and everything has to pass through this, and this was the major part that had failed, the transistors here. Not sure why. Again, I've read that these meters are particularly susceptible to strong RF fields. You know, if you have them in a lab and you've got maybe a ham radio in there or something, maybe that can cook these. Something takes these out that apparently wasn't apparent to the Heathkit engineers when they were testing these. Some operating environment is particularly harsh to this model of meter. And then the power supply and battery circuit down here. So now I'm going to go into my sketches. Well, before I do that, I'm going to just highlight a few things that drove me nuts with this. There's actually a power bus in this thing, B plus and B minus, and normal practice would either just show them with arrows pointing up and down and labeled B plus and B minus and avoid a lot of the clutter, or show them as rails, but instead the draftsman here has them snaking and jinking all over the place, and a lot of times you're looking at something that appears to be a signal path, but then when you follow the zigzags all over, you realize, oh no, that's one of the power rails, and it totally changes what you're looking at. And this circuit here should have been symmetrical, but instead it's drawn this way and this way. It's just, again, bad practice. Almost as if the person was deliberately trying to hide the way the circuit worked from the viewer. This is the minus side of the input circuit, circuit common. And then all of a sudden it appears that circuit common is interrupted by a series capacitor and continues on as circuit common here. Well, that can't happen. That was my first thought when I looked at this. Why would you ever draw something like that this way? Well, in fact, this is the minus side of the power supply, and this is the minus side of the input circuit, and they do have a capacitor between them, but it's not quite as simple as it seems once you realize how the signal gets around and comes back. It casts a whole new light on it once it's drawn in a clearer manner. Anyway, those are just some of the things that drove me nuts, and hopefully I'll rectify in my sketches. Alright, going to talk about the circuit theory now, starting with my sketch of the power supply. You've got a line cord here. The center pin is connected to chassis ground, and that's the only place it goes. There are two gangs of the off, line, and battery switch. These are closed when you're in the line position. You're presenting the incoming voltage across a neon lamp and a current limiting resistor, and then to the dual primary windings of the power transformer. These could be rearranged with jumpers on the circuit board to have the coils in parallel, as they're shown here, for 120 volts, or they could be wired in series for 240 volts. Then you have a single secondary. The one side of it becomes the B minus, the minus side or the negative side of the regulated power supply. And that point is connected through a high voltage capacitor to chassis ground. So there's a reference that's applicable only to AC signals between the chassis ground and the minus of the power supply. There's a half-wave rectifier and a small filter capacitor. The use of a half-wave rectifier and a small filter capacitor is indicative of the fact that there's very little power draw on this circuit. If there was more, this wouldn't provide adequate filtering. Then you've got another gang of the switch that's closed in the line position, and another gang of the switch that's closed in the battery position. So you either have power coming from this source, or you have power coming from the battery, and then continuing on. The battery is an 18 volt battery. It's comprised of 12, count them, 12 C cells in that large battery tube we looked at earlier. There's a current limiting series resistor and a 13 volt Zener diode. That's a first stage lowering and regulating of the power supply voltage. And then that's followed by another stage with a 9.1 volt Zener. And you end up with a approximately 9 volt DC filtered and regulated power supply, the minus side of which is called B minus and the plus side of which is called B plus. And this is a unipolar supply, but the way it's used in the meter circuit, it's more like a bipolar supply, like you might have for an op-amp circuit, for example, where the ground reference is somewhere in between the two of them. And I'll get into that later on. So here's a little sketch which isn't strictly the circuit, but it, I think, illustrates the concept of this meter, the way it's set up. So you've got your probe here, and for the moment let's just pretend like all this meter does is reads voltage. So you've got the center point of the probe coming over here. It goes into some sort of a function select and range attenuation circuit, and that returns back to the common of the probe. So whatever you're measuring here, it's basically limited to just going through here. That's not unusual for volt, ohm, milliamp meters or any subset of that set of functions. What is a little unusual is the way that it continues to the right of this on the diagram. This whole section here acts like a high impedance voltmeter, and again, that's not unusual. That's very typical, in fact, for meters, multimeters. But instead of the common in the front end attenuation circuit being also common with the meter circuit, look at what's done here. The B plus and B minus are treated like plus and minus power rails, and then you've got a voltage divider made out of the zero set pot. That's the big thumb wheel on the front, and this is a simplified version, but this is basically what's going on. So some voltage between B plus and B minus is selected by the thumb wheel, and that point is tied to the common of the input circuit. So we basically, as far as everything over here is concerned, have taken this entire circuit and shifted it up or down in voltage relative to the meter. And that's how we can define different places on the meter that seem to be the 0 point. So then whatever you end up with, the top end of your range, or wherever your signal is relatively higher or lower compared to the power supply, the bipolar power supply of the meter circuit. Now we've got the input buffer voltage follower, and as with all multimeters of this sort, meaning electronic ones, this is a relatively, well, it can be all over the place in terms of impedance. It can be very low, it can be very high, it can be up to 10 megs or whatever. To equalize that out and make it negligible, there will be a very high impedance buffer circuit that, irrespective of how the scaling is going on here, renders the characteristics of that moot and just measures the voltage without changing the voltage. So you follow the voltage here, but you buffer it and isolate the impedances. And this is also powered from B plus and B minus, so the signal coming out of this buffer can be way up towards B plus or way down towards B minus or anywhere in between. And the meaning of the signal that's coming out of it is all dependent upon where the common of the input is placed in the overall voltage span of the power supply. If this pot's right in the middle, then everything is referenced to 0 volts. But if you crank the pot down a little bit, things are referenced to a point below 0 volts. Or if you crank the pot up, they're referenced to a point above 0 volts. And that's how you get that whole zeroing functionality this meter has. Everything can be offset up or down, or if you want to think of it as left or right on the meter. You end up with a signal that's roughly 5 volts full scale. And here you have a differential amplifier, very classic circuit, 2 opposing bipolar transistors powered from B plus up at the top at the collector end, and then they join here and then continue down towards B minus through a constant current source, in this case a constant current sink. So you would nominally have the same amount of current going this way as you have coming this way. The two of them join and go this way. But if this signal here becomes more positive, it turns this transistor on more, so it conducts more, so more current wants to go through it. But since only the current selected by the constant current source can flow, that means necessarily that the current coming out of this transistor must be lower. So as this one increases, this one decreases. Vice versa, if the signal here becomes less positive, this transistor turns off and conducts less, so less current going this way. Since the current coming out this way must always be the same value, that means that more current will flow in this transistor path. And how do we get the reference here? Well, this has got a resistor voltage divider between B plus and B minus that places the base of this transistor at roughly 5 volts, which again is comparable to the voltage coming out of the buffer when you're at full scale. So nominally you'd have 5 volts on each side. Both transistors conduct the same amount. An equal amount of current goes both. There's my air compressor in the basement just kicked on. I'll wait it out. So this differential amplifier is basically doing the mirror image of what this side is doing. So this side goes down while this side goes up, and vice versa. a voltage is developed anywhere in the voltage divider here. This is like a voltage divider, this is like another voltage divider, and the voltage measured at any one point in the voltage divider, say here or here, changes depending on what the current is through the voltage divider. So these 2 points have different voltages on them, and then the meter is connected across these 2 points. If both of these transistors are conducting the same amount, then there should be the same voltage at these 2 points, and therefore the voltage across the meter would be 0, and it should read 0. But if one transistor conducts more due to a larger or a more positive signal here, the other one conducts less, you get a difference in voltages between these 2 points, and therefore current will flow between them in one direction or the other depending on which one's bigger, and that will cause the meter to swing to the left or swing to the right. And how much it swings is controlled by a series resistance that's adjustable, and that's the calibration pot. Now, I simplified this. In reality, there's a different calibration pot for each of the functions, and switching takes care of selecting which of those pots is put into the circuit. Also, it's not a great idea to put the resistive load or the current stealing load of a meter movement at this point in this differential amplifier. So in reality, there's another pair of buffers. The voltage here is buffered by a voltage follower transistor that would be over here somewhere, and likewise the voltage at this point is buffered by another voltage follower transistor, and it's the output of those transistors that the meter is actually tied across. But for simplicity, I left those out. So that's the concept of how the meter works. Now let's get into the details. Alright, here's my sketch of the DC volts function. I'm not going to worry about everything downstream. I go only as far as the buffer amplifier over here. So we start out here, we've got our DC volts being measured. For DC volts, we're using the probe that has the 1 meg resistor in series with it. And the common of the test leads comes down here and becomes the circuit common for the whole front end circuit. The center point of the test probe jack, if the function is selected to volts, and if we're selected to one of the DC positions, either DC minus or DC plus, then the signal can pass through this way, and it's applied to part of the large voltage divider that I showed in the main schematic. This is only part of the voltage divider. There's actually resistors going down and resistors going up from here, but we're only using these many resistors for the ohms function. Now where I drew 1K down here, that's actually 9 resistors in this position, but added up they come to 1K, or 1 kilo ohm. Notice that they're in orders of magnitude, so 6.838 mega ohms, 2.162 mega ohms. Then we drop in order of magnitude, 683.8 kilo ohms, 216.2 kilo ohms, and so on, going down in orders of magnitude. And that gives us the 0.15 volt full scale, 0.5 volt full scale, 1.55, 1550, 150, 500, and 1500 volts. Whichever one we've selected allows us to tap off a different point of the divided voltage. So if we're only measuring 0.15 volt full scale, then the attenuator is just a load on the circuit, but it's a very high impedance one. I haven't added it up, but I imagine you'll get about 10 mega ohm from top to bottom, and that's pretty typical input impedance for a multimeter, and has been for a long time. So it shouldn't load the circuit that much because it's a fairly high value. Again, if you're in this range, then you're just tapping off the original signal with no attenuation. But if we go down to here, for example, on the 1.5 volt range, now because these two add up to something that's 10 times what's below it, you get 1/10 of the original voltage. Therefore, 1.5 volt presented up here is the same as if you were getting 0.15 volts up here. So everything gets whittled down the further you take the selector switch. And that brings everything into a narrow and low voltage range. Now if you're again in DC plus or minus position and you're in volts, then you have another 1 megohm resistor in series with a capacitor going through a switch to the B minus, which is the minus power supply of the meter circuit, and this forms a little input filter. Now there's input voltage protection. These are actually made out of a couple of transistors, and due to the way they're wired up, they function. One of them functions as a regular diode, the other one functions as a Zener diode. So it's just, again, two BJTs, or bipolar junction transistors, and this guy acts as a somewhere in the 5 to 10 volt range Zener, and this one acts as a regular diode. Not especially high power, but it doesn't have to be, because the current is limited by 1 mega ohm in series with 1 mega ohm. So even with a pretty good overload on the input, the current through these diodes would be pretty low. If the voltage is just higher than the forward voltage drop of this diode, somewhere in the 0.6 volt range, for example, then it will start conducting, and it basically shorts the input back to common, thereby protecting the meter from anything too high in this direction. If you have a negative connection that's more than enough to conduct through the Zener diode here, then it goes the other direction. And I should point out that the fact that this is wired as a Zener diode probably doesn't have much of an effect, because if the voltage here is positive relative to common, then it's just going to go through this diode. It's not going to be high enough to bias the Zener into its conduction range. And if you have the polarity reversed, then this is just going to look like a regular diode going in the other direction. So that's basically two diodes pointing in opposite directions to clamp the input voltage, or the voltage at this point, to a safe value. And as this circuit is designed, a 0.15 volt signal at this point will result, at least nominally, in a full-scale meter travel. So again, you shouldn't even get above about 0.15 volts here if you've got your ranges selected correctly. But if you get up to about 0.6 volts or 0.7 volts, one or the other of these diodes is going to start conducting and short the input out. So here we have a buffer, an FET connected in this way, acts as a high impedance buffer, and it's connected as a voltage follower, or as a source follower, as it's called with FETs. So the output here is just a copy of whatever's coming in on the gate, but it's been modified slightly here. Instead of just having a resistor from the source to ground or to B minus, instead there is a constant current source here. Since it's on the sinking end of this circuit, it's really a constant current sink. When you hold the bipolar transistor's base at a constant voltage, then it conducts in such a way as to keep a constant current flowing through it. So that, along with this FET up here, results in a signal coming out of here that should nominally be in the ballpark of 4.9 volts or 5 volts for a left-hand zero indication on the meter. And as I already pointed out in the simplified sketch, this goes into one side of the differential amplifier, the other side of which is held at a constant 4.9 or 5 volts. So when you have, let's say, 5 volts here and 5 volts on the other side, then both halves of the differential amplifier are conducting the same amount. Therefore, there's no difference in voltages at their collectors. Therefore, there's no voltage through the meter. Therefore, the meter is at its left end of travel, basically reading 0 most of the time. But again, if you turn the 0 set pot here so that it skews everything up, now a signal of 0 here becomes higher, and now it causes this to conduct more, and you end up with a higher voltage here for what would essentially be a 0 coming in here. That's how you can get the meter in some modes to read 0 center instead of 0 left. And let's see, oh yeah, so I said before that the offset, or where you define 0 to be, is due to the 0 set thumb wheel in the front panel. And I showed it in the simplified sketch as just a potentiometer between B plus and B minus. In reality, for scale reasons, there's a so-called DC bias adjust. It's a dual potentiometer wired as a rheostat on both sides. And so one adjusts up while the other adjusts down when you turn the shaft. Or if you turn it the other way, the one that was adjusting up now adjusts down, and vice versa for the other one. So essentially what you're doing is you're taking this pot and electrically moving it up or down, more positive or more negative, and therefore its center point, wherever that is, also becomes more positive or more negative. And then for various reasons it's also necessary to throw a little kink into the operation, so there's an additional resistor on the plus side here that always biases a little bit more in one direction than the other. So that's the basic functionality of the DC volts input. Here's the AC attenuator, which is really, as I notated here, only used for AC volts. If you're in AC milliamps, or well, if for example, if you're in AC milliamps, in other words in AC but in milliamps as well, the signal is switched to pass directly through this circuit without being modified. So even though the circuit may include this, it's not doing anything if you're in AC milliamps. So once again we have, and I should say this whole circuit here replaces the circuit I already described for measuring DC volts. It's an alternate circuit. So you've got your input coming in. This time you're using the AC probe, so there's no series resistor out here like there was with DC volts. And if you're measuring volts and you're in AC, the signal goes through this way. And there's also milliamps if you're in AC going by this route, in which case there is a resistor from this point back to the input common, and that's your resistor shunt for the milliamps function. So if you're putting a current through here, then the current would flow this way, and you would measure a voltage across this shunt resistor through this circuit. There's a DC blocking capacitor here, and then here's our attenuator. There's actually two stages to the attenuator, this one up here and this one down here. So only part of the work is done by this one. This first stage attenuator has the first 3 positions all wired together, the next 3 wired together, and the last 3 wired together. So there's only 3 stages of attenuation here in this voltage divider, and each one has a parallel capacitance. Only the lowest, or I'm sorry, the highest voltage ranges are not adjustable in this regard. It's a fixed capacitor. But if you're up in the middle ranges, then you have an adjustment capacitor here for some compensation of AC signals passing through this simple resistor divider. And then finally there's another adjustment cap across this resistor. And these are the ones I said where Heathkit's calibration instructions say if you don't have a function generator and an oscilloscope, you can't really set these up, so they just tell you something like, you know, turn them to the mid-range or something. That's the nominal value anyhow, so it gets you pretty close. So again, even if you're measuring milliamps, AC milliamps, your signal still comes up here. It still has the DC component blocked, if there is any, but it's not affected by this attenuator because in milliamps it bypasses the attenuator through this switch. Only if you're in volts mode does this attenuator's attenuation function produce a reduced signal or attenuated signal that comes through this gang of the volts position switch. So that's how come I'd said before that when you're in AC milliamps, this circuit doesn't really do anything, doesn't modify the signal. And here you have a series resistor with a capacitor across it, just a little bit of conditioning. And this is really a current limiter for the overload here. So here's two more bipolar junction transistors, or bipolar transistors, wired as Zener diodes. And whether or not you think of them as Zener diodes, or if you think of them as just forward bias diodes, regardless of the polarity here, if the voltage here gets to be too great, one or the other of these will conduct and short the signal back to this point here. Well, this doesn't seem to go anywhere. You'd expect it to go to common, but it doesn't. Anyway, so the signal here, which is an AC signal still, there's been no rectification here. It gets buffered by this circuit, which is again a high impedance buffer circuit that's a voltage follower, or in FET lingo, it's a source follower. So the voltage here follows the voltage here, but this is a high impedance and this is a low impedance. Then once again we have a series capacitor here to block any DC component that may have crept back into the signal, so we have only AC coming out, and that gets fed into the second stage attenuator. In this case, unlike here where each set of three ranges were grouped together, the second stage attenuator works on it oppositely, where the first in the group has a dropping resistor, the second one has another dropping resistor, the third one has another. So even though this stage treats these three ranges identically as far as this attenuation goes, once it gets to this stage, there is additional attenuation that's appropriate to these three stages, and then the same thing applies again for the next three, and the same thing again for the last three. So a two-stage attenuation. Once again, if you're in milliamps, AC milliamps, but just milliamps, whether it's AC or DC, the signal bypasses the attenuator. So as I said before, measuring AC milliamps, this attenuator circuit does nothing. The signal just passes through. But if you're in volts, it comes out of here, and there's actually a switch here which isn't really part of the AC attenuator circuit, but it appears in my other sketches. If you are not using the AC attenuator, you don't want it messing up the signal going to the high impedance voltage buffer circuit. The signal comes out of the attenuator and passes through yet another DC blocking capacitor on its way to the buffer. But if you're not in AC volts mode, then one of the DC switches is closed and this point is dragged down to B-, and then this capacitor, instead of being a DC blocking capacitor, becomes a filter capacitor on the signal. And so when you're measuring DC volts, DC amps, etc., the signal is actually coming in this way, and it sees this resistor in conjunction with this capacitor to be minus, acts like another filter stage. But when we're in AC volts, this switch is open, and this capacitor does double duty as an additional DC blocking capacitor. Now, it's critical to always maintain a voltage reference for all this stuff. We know that when we were in DC volts, the common side of the input was given some sort of a voltage reference to the meter circuit by way of the zero set potentiometer, and that's still true. The zero set potentiometer circuit is still here. The wiper of that zero set pot is still tied to the meter's input common, so it's exactly the same as if it was measuring DC volts. And this reference voltage is also connected through a 10 meg resistor, but only again if you're in AC and in volts. So a bit of switch logic going on there. And that voltage reference point also comes through here, and this is the 1 meg ohm resistor, which signals usually go through on their way to the high impedance buffer circuit. But when we're in the AC volts mode, that's just providing a DC reference to this point that still establishes the zero. The zero set does work on AC voltage measurements. So we've established a DC reference here, and then on top of that we superimpose the AC signal coming out of the AC attenuator. So that signal, even though the DC component coming through this way has been blocked by all these series capacitors, we reintroduce a DC offset at this point, and that DC offset comes from the zero set control. One more thing. The bottom side of the first stage attenuator, but not the second stage, which goes to B minus, but the bottom side of the first stage attenuator and the voltage clamping diodes, it returns to a point which is held between B plus and B minus, very much like we did here, but it's only for AC volts. It works in conjunction with the zero set to establish an artificial reference point for the first stage attenuator, and that's called the AC bias. So that doesn't replace the DC bias, which is always there, but it adds to it for the first stage attenuation. Confused yet? Had me scratching my head. So you're probably asking yourself what I asked myself. Where the heck is the AC to DC converter? Or the AC converter, as it's often called on multimeters. There has to be something that converts the AC signals to DC so that the rest of the circuit can handle them. Well, not yet. In this particular multimeter, the rectification is about the last thing that happens in all the stages that the signal goes through. So this stage provides no rectification of the AC signal. All it provides is the attenuation. And when we come out of this stage, as I said before, we have a DC bias voltage with an AC signal riding on it. If this point is 0 volts DC, then the AC signal rides equally above and below 0 volts. But if we've adjusted the zero set to, say, 1 volt, now our AC signal is riding on a 1 volt DC signal, so it's raised up 1 volt. And that's applied to the input buffer, which can handle alternating signals. So it can handle AC or DC, and it does its job, and it remains, at least on AC volts, it remains that way all the way up until you finally apply it to the final stage meter driver circuit, which is where it gets rectified if it needs to be. Okay, let's look at DC amps. It's important to point out at this point that the test probe that Heathkit provided with the IM-25 is the same test probe that they used for all their vacuum tube voltmeters, or VTVMs, which can only measure voltage and resistance. They do not measure current. And the labeling on the probes is DC for one position, which has the 1 meg resistor in series with the signal, or AC/ohms, which has no resistor. That's fine until you try to use it with the IM-25, which also has the milliamps function, and also has a very different front end for some of the signals than the vacuum tube voltmeters do. It turns out, and Heathkit's manual actually says this, you use the probe that's marked DC, or the position on the probe that's marked DC, only for DC volts, not for DC milliamps, nothing, just DC volts. For everything else, AC volts, milliamps, whether AC or DC, and ohms, you use the probe position that does not have the resistor in it. Accordingly, I show in my sketch that there is no resistor on the input. So we've got an external current that's passing through the meter. It's going to come into the meter, come around, go back out, and we're going to measure it. So if you're in the milliamp function position, this switch is closed. The current comes in here, and it's applied across this portion of the big resistor divider, all the way back down here, and then back on out the jack and on its merry way. And because of the resistor or resistors that are brought into effect by the range switch, you drop a voltage across the resistor divider, and that's tapped off right here. Whoops. That's tapped off right here. And if you're in DC and the milliamps position, then the signal continues through the 1 meg resistor, and there's this filter capacitor, which I already mentioned gets used as the output DC blocking capacitor for the AC attenuator circuit. But in this instance, when we're in a DC position, whether it's DC minus or DC plus, this capacitor is instead connected to the B minus power rail, so it acts like in combination with this resistor, it acts like a filter element, while at the same time the resistor here, along with the two transistors connected as Zener diodes and or as regular diodes, limit the voltage at this point in the circuit, and that returns back down here to the common of the input circuit of the meter. So that's all very straightforward, just like pretty much any multimeter circuit. You run the current through a shunt and then you measure the voltage developed across the shunt. Well, if you're only measuring 0.015 milliamps, then that current has to go through all of these resistors, which is a lot of resistance. But because it's a lot of resistance, even that small current develops a fair amount of voltage across it, or at least enough voltage to satisfy the rest of the meter circuit. But if, for example, you're measuring 1.5 milliamps, now the switch connects down here, and none of these resistors are part of the circuit. So you're dropping, or you're running the current through a lesser amount of resistance, and therefore the voltage developed across that and tapped off here is less than it would be, but because there's more current, it ends up being in the same range. And once again, the goal is always to get the wide variety of signals out here scaled down so they all appear in the same range for the rest of the meter circuit. I've just redrawn the input buffer here. It's exactly the same as it is for the voltage mode. It still has the same constant current sink here, and it acts as a source follower, so it just isolates the impedances from one side to the other, and you end up with a roughly 5-volt signal out here when you should have a full scale according to the input signal and the selected range. So this FET does provide some gain, because normally there's only 0.15 volt or whatever it is. Here, yeah, 0.15 volt here results in full scale meter travel. So that has to be amplified up to about 5 volts by this buffer. And it wouldn't do that if you don't have additional current going through it, and that's what this has to do with. Anyway, so otherwise it's exactly the same. You still have the 0 set, just like on DC volts, that establishes where in the overall bipolar power supply the common of the input is. Therefore, taking whatever voltage we're dropping across the shunt resistors and raising it or lowering it relative to the voltage span that the rest of the meter is expecting. So here's the ohms function. Once again, the probe has to be set so that it does not have a 1 megohm resistor in it, and therefore the resistor under test is the only resistance that's external to the meter. Now, before I show this whole thing, I'm going to show my ultra simplified version of it here. You basically have a current path that goes in a loop like this. This is all internal to the meter. It does not include the external resistance. There's a fixed 10 ohm resistor, which is actually the bottom 5 resistors of this big voltage divider. All of those bottom 5 resistors add up to 10 ohms. So that's this. And then you've got that in series with the 3-volt battery in the meter. This is one of those that still needs to be there even if you're running the meter off of line power. This provides the excitation voltage to get current going through the resistor under test. And by doing that, developing a voltage across it which gets measured by the rest of the meter circuit. But, you know, this voltage from this battery, who knows where that's at. You need to regulate the current so that the current is always the same, and therefore you can do a simple Ohm's law conversion to calculate the voltage dropped across the resistor under test. But we're not even at the resistor under test. We're just looking at this part of it. So we're just looking at that internal 10 ohm resistance. So to get that constant current, there's a small constant current circuit here comprised of a bipolar transistor and a small resistor. As mentioned elsewhere here, when you connect a bipolar transistor in series with another circuit and you hold its base to emitter voltage constant, then the current through the collector to emitter is held constant. So this regulates the current in this loop in such a way that you end up with a constant 0.07 volts dropped across this resistor here. But now we want to actually measure an external resistor, and the way that's done is you have all these other resistors in this big resistor voltage divider that gets used for all the functions except for AC volts, and it's represented here just as a simple adjustable resistor that's in series with the resistor under test, which is external to the meter, and the series combination of those is in parallel with the 10 ohm resistor. And so some of the current goes this way and some of it goes this way, but the constant current source is always trying to maintain the same overall current. So from here to here, all these resistors combined in parallel, you still get 0.07 volts. The thing that's squirrely about this circuit, and I've never seen it done this way, is putting an external resistance under test across a fixed resistor in the meter and trying to, by measuring the voltage essentially across that resistor under test, expect to get a proportional value related to the resistor under test. Well, the answer is you don't. As soon as you start putting that in series with a fixed resistor, that's the range, and then putting that in parallel with a fixed resistor here, which is also part of the range circuit, the result is going to be non-linear. So you end up with what I already showed when I was demonstrating the meter, that you start out with, at the low end of the meter, when you're measuring ohms, and everything is spaced way out, and the further you go to the right, the more compressed it gets. And that's the result right here of doing that parallel resistance operation. But it does work out, and the meter is scaled appropriately so that when you do this goofy thing, you do get an appropriate deflection on the meter, and it's going to point to about the right resistance. The problem is, because of the goofy way they've done this, you end up with a very non-linear meter, and that just makes everything harder. It just makes life complicated. It makes it harder to read values that are more upscale on the meter. And I think Heath just totally boogered this part up. It's, you know, who passed off on that? Who signed the document saying this is ready to become a product? I don't know. They could have done this differently, and the world would have been a happier place. But that's what's going on. So now, looking at the full circuit, it's really just the same as I simplified here. We have the incoming, well, we've got the resistor under test going through a switch which is only closed in the ohms range, and then that's in series with however many of these resistors are switched in by the resistance range switch. And then that is placed across this internal 10 ohm resistance. And if we ignore the external part of the circuitry, then we have this loop here with the 3-volt battery for the ohms excitation. That's in series with the internal 10 ohm resistor, assuming you're in ohms mode. And that's in series with the transistor of the constant current source. It's near the 4th of July and people are already setting off fireworks outside. I don't know if that was picked up on the audio. And the current then continues on and goes back into the 3-volt battery. So we've got just what I illustrated here, but just laid out a little differently. The 1.35 mercury battery, which is the third battery in this meter, once again, if you're in ohms mode, is switched into the base of this transistor to make it act as a constant current source. And otherwise it's exactly as I described it over here. Just like I said here before, this point, which is almost an arbitrary point in the loop, but it's essentially at the bottom end of this resistance, and that's connected to the 0 set pot, so you can reference this whole thing up and down relative to the midpoint between B plus and B minus. And that's shown in a fuller version here, but it's the same thing. And once again, we have the transistors that are acting as clamping diodes. Once again, we have the 1 meg resistor that's connected into the measurement circuit, and with a capacitor to B minus acting as a filter, and the resistance once again also acts as a current limiter for the protection diodes, which again are made out of bipolar transistors. And again, it's that signal is ultimately applied to the high impedance buffer amplifier circuit, just like with volts and with milliamps. So this is one of the many things that had me stymied. The way they drew this circuit on the original Heathkit schematic was so misguided or incompetent or something that it was really hard to figure out how this worked. But when it was drawn, well, like this originally, and then just for convenience I drew it more laid over on its side, but it's the same thing, it makes a lot more sense and it's a lot easier to figure out how it works. Okay, the last sketch. This is the meter driver circuit. It takes the output of the high impedance buffer amplifier, which all of the functions have had in common. And again, we're expecting about a 4.9, Heathkit says, or more like 5 volts. It's not really important exactly what it is because it can be adjusted by the zero set control. You have a differential amplifier here, a classic differential amplifier, and it's made out of these two transistors, each with the same value collector resistor from B+, and through equal value emitter resistors coming from the emitters, and those are connected together, and the current that flows through here and the current that flows through here are summed up at this point, and together they flow through this transistor down to B-. And once again, this is a transistor that's got its base to emitter voltage held constant because there's a resistor from B+, and then there are two diodes in series going to B-, and there's a constant voltage drop across these diodes that gives you roughly 1.2 volts here on the base, and that establishes the constant current that this is going to make sure it passes. It's always going to make sure that you've got that current going through it. Now these aren't really diodes, they're in fact two more bipolar transistors of the same model that this is, but they're only using two terminals of them, and they're wired in a way where they act like two diodes. Because this is a differential amplifier, the way this works is we have to also hold this transistor's base to some voltage. Well, there's an additional voltage divider here from B+ to B-, 18K here, 22K here, plus a filter capacitor around the lower one. It just holds this point very steady, and it's designed to hold this to roughly 5 volts. Heathkit says 4.9, but again, that's subject to a lot of variation. It depends on, you know, if you're running it off a battery voltage. Are the batteries depleted? Are they fresh? It's not really important. The important thing is that this point is held constant, and that voltage here should match the voltage coming out of the buffer amplifier when you have no signal. So when you have, for example, 0 volts coming into the meter, if you're measuring voltage, you should end up with the same voltage here as there is being held constant here, and that means that both of these transistors are being turned on by the same amount, therefore they conduct the same amount, and therefore because there's a constant current sink down here, the current going through this one is identical to the current going through this one. Now if the output from the buffer amplifier goes more positive than 5 volts, then it turns this transistor on a bit more, and therefore it conducts more, and there's more current going through it. But because this insists that there only be a fixed current which cannot go higher or lower, if there's more current going through this way, then there must be less current going through this way. Even though the base is being held constant, there will be less current going through here. Now voltages are developed at the collectors, and if both transistors are turned on the same amount, you'll have the same voltage here as you do here. And that is applied to these driver amplifiers, which are just simple transistors with B plus on the collectors and a resistor to B minus on the emitters, and the voltages dropped across these resistors should also be equal, assuming you have a reading of 0 in mind, or a reading of 0 is appropriate at that moment. If this differential amplifier starts seeing more current here and therefore more voltage, then this side should be seeing less and therefore it's going to have less voltage. That will turn one of these transistors on more, so more voltage across this resistor, and the other one will be turned on less, so less voltage across that resistor. Therefore you have a different voltage from here to here, and through all this switch wiring, the meter is essentially connected across these 2 points. And if they have the same voltage, then there's no current, therefore there's nothing going through the meter, and it will read full left on the meter. Once you start unbalancing the differential amplifier here, and therefore unbalancing these 2 points, or these 2 points, now you start getting some voltage flowing from either here to here through the meter, or from here to here through the meter, depending whether the signal is greater or less. And to get the correct reading on the meter, there's always a series resistance. If your switch is in, for example, milliamps, it's going to be using the same calibration that it uses for volts. So let's look at volts. If you're in DC volts or DC milliamps, then this potentiometer is put in series with the meter movement between this point and this point. And by adjusting that, you can determine what the full scale value will be, and thereby calibrate it for anything with a DC signal, except for ohms. If you're measuring AC, then the switching here puts this trim potentiometer in series with the meter instead of this one, and that's how you can calibrate it for AC. If you're measuring ohms, once again, the switching puts this pot in series with the meter instead of one of those, and you adjust that as the ohms cal. So it's really that straightforward. Now, when you're measuring plus or minus DC, that switching of polarities occurs here only at the last stage. Everything else is still going positive or negative depending on what the input's doing. But if you have the polarity opposite from the way you'd like it, then you switch the AC, or the AC DC minus DC plus switch to the other DC position. It just takes the meter and flips its polarity around relative to everything up here. Therefore you get meter deflection in the other direction. Now if you've taken the 0 set thumb wheel, which is common to all functions, and adjusted it such that it's skewing every voltage here up or down, you can establish 0 as being at a different point, and maybe then the meter has got 50% deflection when you have a 0 input to the meter. And that's already been demonstrated in the demonstration part of this video. And finally, the rectification I mentioned earlier. If you have an AC signal, whether it's AC volts or AC milliamps, all the signals up to this point are still AC. They may be more or less offset, positive or minus, due to the action of the 0 set potentiometer, but it's still an AC signal. It's going up and down. Well, that's a semantic issue, right? It's not actually changing polarities in the meter circuit. It's just more or less positive, but it's still got the same waveform. That is ultimately, when you're in AC volts or AC amps, the signal is run through this diode bridge before being applied to the meter. And therefore the AC cal cannot be the same adjustment as the DC cal, because you have to take into account the voltage drop of the diodes in the diode bridge. Otherwise, if you didn't have that, then you could probably just have one calibration pot for everything except ohms, and then have the other one for ohms. But because of the fact this diode bridge is introduced into the meter circuit on AC volts or AC amps, you need to have a separate AC cal pot to compensate for that. But that's really everything that's going on here. That's the entire meter circuit.